equations for this line. How do we do that?
Solve for t.
Solve each of these for t, and then set them equal to one another. So for part C, let me do symmetric. Let's see, are y'all okay with me solving this for t mentally? Is that okay with you? I'm going to move the 3 over and then do what? Divide by 4. So I should get x minus 3 over 4, right? That's equal to t. And then this one, move the 6 over and divide by 8. So this is my other equation. Y minus 6 over 8 equals t. And then lastly, z plus 4 over negative 3 equals t. Those are all equal to one another. So I'm going to put that up here. X minus 3 over 4 equals y minus 6 over 8, but equals z plus 4 over negative 3. Do y'all see how that's just like an extension of what we just did in R2? Right, there's just that third thing now. All right, so now I have a much more interesting question that would have been a lot harder to do without all of this. So I gave you 2 points, right? What were the 2 points? They were those two points in three-dimensional space. Yes? 1 and 2, line between the two. Now what I'm asking is, can you find where this line hits the YZ plane? All right, so let's see here. RGB, right? Red, green, blue. RGB. So that's the X plane, or X, this is X axis, Y axis, Z axis. I want to know where this thing hits the YZ plane. So this sheet of paper right here, we're talking about this plane right here. I want to know where this line hits that. It hits this plane at a point, doesn't it? Mm-hmm. I want to know what point that is.
So set that equal to 0 then?
Set what equal to 0?
X minus 3 over 4 equals 0.
You set this equal to 0? Why?
You want to find where the x component is 0.
What are you setting equal to 0?
3 plus 4.
If this line, hold on, if this line is hitting this plane, right? It's going to hit at a point. What can you tell me about that point? There's something in particular about this point. If I'm on the YZ plane, what can you tell me? What is 0? Your x coordinate has to be 0, right? If I'm on this plane, then my x coordinate must be 0, shouldn't it?
Because we're not a vector.
So if my x coordinate must be 0, is there anything up here that tells me about my x coordinate?
There's a lot up there.
There's a lot up here. But this one right here is really nice, isn't it?
Yeah.
That tells me about my x coordinate. And I want to know when that x is 0, don't I? Yes.
Is the x coordinate the same as the x component?
Wait, is the x...
Coordinate the same as the x component? I know it's different.
So what I'm saying is when this line hits this plane, it hits at a point, doesn't it? And that point has an x coordinate of 0. And in my big like overflow of information here, the one thing that tells me a lot about my x coordinate is this parametric equation right here. It tells me x will be equal to this. And if I know that the x must be 0, then I can solve this equation for what? Well, you set x equal to 0, don't you? And you solve this for t. And once you know t, then you can use the original vector equation right here to give me the point, right? Does that make sense? You figure out from the parametric what's going to give you an x coordinate of 0 on that point. And then from that you recover the t, and then you use that t to recover the other coordinates. Let's do it. So the YZ plane means that x must be 0, right? That's what the YZ plane means, that your x coordinate must be 0. Yes?
Why would you use the one from B and C is already solved?
Well, either one. It doesn't matter which one you use. You could use this one or this one. Totally up to you. You're saying why? Because this is already solved for t, right? I agree. This one, I could just plug in x0 here. It really doesn't matter. I mean, they come from the same place, right? They both have x. They both have t. They're just rearranged. So it doesn't matter which one. I just said this one is kind of glaring because it's actually the equation for x, right? And if I know x is 0, then boom, I'm going to use that one. But feel free to use this one. So if x is 0, then what I can do is I can use that, right? Using, again, your choice. I'm going to use that equation right there. I use that, and I replace the actual x value with 0. If I replace that with 0, I get this. And then if I solve for t, you get negative 3/4, right? And once I have that, I can get the other pieces, right? Just plug in negative 3/4 here and here, and we give you the y and the z respectively, wouldn't it? Yes?
Our y is 0, but our z is not.
Wait, our y is 0?
Yep.
Oh, when you
Y-
plug it in. Oh, you've already plugged it in.
Our y is also
Yeah.
0.
I'm going to actually just plug it in this way. I'm going to go back to the original vector equation that we came up with. And that's this one right here. And what do we know about this? This is 0. We know that already because that was kind of the condition, right, to be in the YZ plane. This one right here, I'm going to replace the t with negative 3/4. And then here, replace the t again with negative 3/4. And that will give me the vector, right? And then I'm just going to convert that to a point. So 0, and then here this reduces out to, this is negative 6. 6 plus negative 6 is 0 again. And then this is not pretty. Negative 4 plus 9/4, something like that. So you can put that together. It turns out that this actually lies where? 0, 0, so x is 0, y is 0, z is, it turns out to be negative, doesn't it? So it's down here somewhere. So it actually hits at the z-axis somewhere.
So it's a z-intercept.
Yeah, it's like a z-intercept.
Do we have the concept of intercepts in 3D space?
Sure.
Oh,
Yep.
We maintain that?
Yep. All right, so recap. To define a line in 2 or 3 dimensional space, you need 2 points. Create a vector R naught that goes from the origin to the first point. Create the vector v, your direction vector, which is a vector that goes from one point to the other. And then you use this formula R naught plus TV. That gives you the generic formula. And then from there you can get your parametrics, and then from there you can get your symmetrics. Yes? When I was taking vector calculus, I actually took a course. When I took calculus, instead of taking 3 4-hour credit courses, right? That's what if you've done all your calculus here, you've had to take 3 4-hour credits. When I took calculus, I took 4 3-hour credits. So we had Cal 1, Cal 2, Cal 3, and then the 4th one was called vector calculus. And my professor, when we learned it, we didn't do this formula, we did this. U plus TV instead of R naught plus TV. So instead of calling it R naught, we called it U, and the rest of it was the same, right? And I remember it because, or he did it that way to help us remember, he called it the couch potato formula. The couch potato. U plus a TV, right? U plus a TV. You sitting there with that's your couch potato formula. Unfortunately, our book does R naught plus TV, so can't use it. But I still remember it that way. Like, even though I teach it that way, that's the way, when I do vector stuff, I use this, U plus TV. All right, what's next? Creating line segments. Okay, this is really important because when we talk about line segments, there's different ways to do it. And a lot of times when I'm working problems out in this class, I'm going to do it a certain way. And if you want your work and my work to make sense, like together, like look back at mine, we need to be using the same convention, or else the way you do it and I do it are going to look really, really off. So right now, if somebody gives us 2 points, right? We have a way of coming up with the whole line, don't we? We can generate the whole line, all the vectors. But what if I only want the points between 2 points, right? So this is, let's say, this is some point, call it P1, P1, this is point P2. What if I only want that line segment right there instead of the whole line? So back in college algebra, that was easy to do, because if somebody defined a line in college algebra, we graph it, right, something like this. Then if I only wanted a segment, all I'd have to do is restrict my x values, and that would restrict it, wouldn't it? I could just get a nice little line segment with just restricting my x's. Here, t is the variable, right? So how do we restrict t in order to just create the line segment, right? Yeah, so there's different ways to do it. The most, I guess, intuitive way is to use this formula right here. There's 2 of them up there that I have written. This is the one that I'm going to use. Which is, there's nothing new here. This is exactly the same formula we've been using, all right? It's this one right here. It's that formula right there. All we do is restrict your t between 0 and 1, all right? Take that, restrict it from 0 to 1, and what it's going to do is it's going to create the line segment that goes from one point to the other. I think I might be able to convince you of this. If you go back to the first example we did, or was it? That example, right? With that one, do you remember when I said, hey, let's create more points? And it said plug in 0, what did we get?
We got our first point.
We got our first point. When we plugged in 1, we got the second point, right? So all the numbers in between would create all the points connecting the 2 points together. So that's the idea. I'm going to let you read this for a second.
Gotcha.
Okay. I've given you 2 lines. Do these lines live in 3 or 2 or 3 dimensional space? 3, right? You can tell because the first line, you have 3 components, right? And notice that in that first line, I'm calling it capital L1. Notice in that first one, I'm using the variable t, right? In the second line, L2, I'm using a different dummy variable. I'm not using t for both. I'm using s for the second one.
So they're scaled.
That way they're not related to one another in terms of the t that draws this one has nothing to do with the t that draws this one. So I don't want to use the same t in both. So these both live in 3-dimensional space, and I'm asking for us to determine that they're skew. That means, first of all, we have to determine that they don't ever intersect each other, and that they are not parallel, and that they are not orthogonal. That's what it would mean for these to be skew. They don't hit each other, they're not parallel, and they're not orthogonal. Yes?
So the plane is parallel, but they're going
No, like this. Okay, these would be skew. That would not be skew. That would not be skew. Hitting each other would not be skew. Is there another question? All right, so let me kind of go about this one thing at a time. And I'm not going to necessarily go in the order that they gave me. the information in, all right? Let me talk about L1 first. Let's talk about that first line. I'd like to write it a different way first. I'm going to write R1 of t equals, I'm going to write it in its vector form first, like this, or an alternative vector form using that functional notation R of t in front. That's my first line, right? Written the way that I've introduced this idea. But from there, I have this. I'm now writing the parametric equations of this line. Right? And then from there, I'm going to get the symmetrics. I don't think I want to do that. See, y plus 2 over 3 equals z minus 4 over negative 1. Okay, y'all following what I'm doing here? Just taking that, solving for t, take that, solve for t, take that, solve for t, and then set them equal to one another. So I've got the vector function, parametric, and symmetric.
Yep.
I just decided to put all these things down here, all right? Let's do it for the other one. For L2, I'm going to write R2 of S equals 2S, 3 plus S, negative 3 plus 4S, and then X equals 2S, Y equals 3 plus S, and Z equals negative 3 plus 4S. Those are my parametrics. And then my symmetrics would be X minus 0 over 2 is S. So I moved the two, sorry, I messed that up. Oh, no, I didn't. That's right. So I didn't have to move anything over. I just divided both sides by 2. But I wrote it as X minus 0 so that you could see the point on top. This one would be Y minus 3 over 1. And then this one would be Z plus 3 over 4.
Cool.
With me? What are the direction? What are the direction numbers of L1? Okay, so what are the direction numbers of L1? Go ahead. 1, 3, negative 1. Got that, everyone? This right here has as its direction vector. We've been using V as the direction vector, right? I'm going to write it as V1 because I want to distinguish it from the direction vector of this one. The direction of this vector is 1, 3, I'm sorry, the direction of this line, the direction vector of that line is that, right? Now, on the second one, what's the direction vector? 2 what? 2, 1, 4. 2, 1, 4. Everyone got that? 2, 1, 4. So there's different ways you can get the direction vector. One way is to look at the coefficients in front of t. You see that? 1, 3, negative 1. That's one way to do it. You can get it from the denominators, the denominator of the symmetrics. There's various ways to get your direction numbers, all right? Just like in this one right here. What are the coefficients of S? 2, 1, 4, right? 2, 1, 4. Or you get it from down here, 2, 1, 4. Why do you think I found the direction vectors for these lines? You can see if they're parallel, right? Immediately? What do y'all think? To be parallel, what is it about these vectors that has to be true for two vectors to be parallel? They have to be scalar multiples of one another. Are these scalar multiples of one another? No. How can you tell that they're not scalar multiples? Yeah, you have to basically just say, hey, look, how would I turn a 1 into a 2? What would I have to multiply by? By 2, right? But then 2 times 3 is not 6, so they're not scalar multiples, right? So I can say they're not parallel, right? Are they orthogonal, right? Are they orthogonal? What do you do there? Dot product. Take these two vectors, right? If you have two lines and you have their direction vectors, then for them to be orthogonal, right, would mean that the dot product of those direction vectors would have to be 0. So let me start writing this stuff down. So I'm going to say here, L1 is not parallel to L2 since V1 is not a scalar multiple of V2. See how I wrote that? V1 is not a multiple C times V2. They're not scalar multiples of one another. L1 is not orthogonal to L2 since V1 dotted with V2 is, now I didn't do that, I didn't do it and I just erased V2. Let me put it up here. What was V2 again?
214.
214? I guess I could have looked up there, huh?
Yeah.
214. Okay, so if I ask you to dot these, you go this times this, right? 2 plus 3 plus negative 4. 2 plus 3 plus negative 4, but that's not 0, right? You need it to be 0 for us to be orthogonal, right? Questions on that? We're not done with the problem, but questions on those first two things. Parallel and perpendicular, pretty straightforward. All right, convince me that they don't intersect one another. That's harder. How could you convince me that these two lines don't hit each other? So say what? How do you mean?
Solve both equations for t, and if they're both equal to a solution, then
But one of them has S, one of them has T, so I don't know, I'm not quite sure I'm following you. Right?
Could we set T and S equal to each other?
How?
See if we can find a value where they could be equal?
Yes? Say, I heard something over here.
I said we would set both the x components equal to each other, so 1 plus t equals 2s, and then solve to see if t equals s.
Yeah.
So when t equals s?
So this is correct. Look, if these lines hit each other, then they're going to have the same x, y, and z point. There's going to be a point, right, where they hit, and that point will have the same x, y, and z value for both lines. So you're trying to ask yourself, are these ever equal? Are these ever equal? And this and this and this, are those ever all equal to one another, right? At the same time. You need it to be at the same point in time, right?
Yeah.
So I'm gonna try and write this down so you can kind of follow. This is the hardest part of this problem. So, do they intersect? Do they intersect? Well, is there a T and S such that what? We need the x components to be the same at the same place, right? So we need 1 plus t to equal 2s. 1 plus t must equal 2s. Is that the only condition we need? And we need the y components to be the same. So and what? Negative 2 plus 3t must equal 3 plus s, right? So we need the y components to be the same. There's some s and t that are going to make the x components the same, the y components the same, and then finally, we need the z components to be the same. Who has a question? Someone have a question? trying to figure out, is there a t and an s that are going to make the x's, y's, and z's all match? Right? So we need all three of these to be simultaneously true. So what we have here is a system of equations. We have how many equations? 3. How many unknowns?
2.
Okay, if you have 3 equations and 2 unknowns, what types of answers can you get? You're going to have a free variable, right? At least one free variable. So we might have more than one answer. How would you go about solving this? Do what?
Solve for S first, or T first.
Okay, so you want me to solve for one of these for S or T, and then, so you want me to do like substitution or something like that?
Yeah.
Okay, but I have 3 equations, don't I? But I only have 2 unknowns. Yes?
You could add the first equation to the last equation.
Okay, so you could do elimination, right? You could do elimination. So there's different approaches at this point. The way that I'm going to do this is I'm going to do it like this. Do you agree that those 2 have to be the same at the same time? I mean, forget the third one. At least those 2, right? So what I'm going to do is I'm going to treat this like a system of 2 equations and 2 unknowns. That's going to have some answer, perhaps, right? And then what I'm going to do is I'm going to say, okay, that's what make those 2 true. I'm going to see if that works in the third one. If it doesn't work, then what? They don't hit each other. That makes sense? So let's do it. Take this first one. I'm going to treat it like a new system. 1 plus t equals 2s. And then negative 2 plus 3t equals 3 plus s. And I mean, you know, there's all sorts of ways you can mess with this. You got your linear algebra background, you know, whatever. I'm going to just go back to more of like a college algebra, no matrices, just old school, I guess. Negative s plus 3t equals 5. Let me just double check this. All I'm doing here is moving all my variables to one side. So negative 2s plus t equals negative 1. I messed that up. Negative 1. I almost screwed that up. All right, so bring your 2s over. Take your 1 to the other side. It's our first equation. Here, bring this s over. Leave the 3t. Add 2 to both sides. Y'all okay with that? 2 by 2. 2 equations, 2 unknowns. I'm going to use elimination just because I favor elimination over substitution. So I'm going to multiply. I have choices here. I'm going to multiply because I'm up here, I'm in control. So I'm going to multiply the second equation by negative 2. That way I'll get my s's to cancel. So when I multiply my second equation by negative 2, I get 2s plus t equals negative 1. And then the other equation becomes positive 2s minus 6t equals negative 10. And then when I add straight down, what do I get? Crap, not a nice number. I get negative 5t equals negative 11. So t is 11/5. All right with that?
Yep.
So the only way that these 2 equations will be equal to each other, the only way, is if t is 11/5. Once you know t, you can go back and get s, right?
Yeah.
So I'm going to go back to these equations. I'm going to just go back to the first one here. I'm going to replace the t with 11/5 and then solve for s. Okay, so 1 plus, I'm using this now, 1 plus 11/5 equals 2s. 16/5, right? 16/5 equals 2s. And then divide both sides by 2. 8/5. I reduced already. 8/5 is s. So if there's any hope that these 2 lines are going to intersect, if there's any hope at all, then the t would have to be 11/5 and the s would have to be 8/5, right? But that only solves these 2. So now what I'm going to do is I'm going to take those 2 answers, and I'm going to plug them into this third equation and see if it's true. If it's true, what? If I plug in t and s here and it's equal, then what does that mean? They do intersect. But if it's not, then what do I say? They don't, right? And that's it. We're done looking. Now, it turns out that they don't. Okay? I mean, because I said in here, determine that these lines are skewed. So I was telling you they were, but you had to verify it. So we have to show they're parallel, we have to show they're not they're not parallel, they're not orthogonal, and that finally they never intersect each other. I'm going to leave the end of it for you. Just plug in 11 fits there, plug in 8 fits here, show that it's not equal. You know they don't hit each other. I'm almost out of time.
Time flies when you're having fun.
Yeah, well. Do we have any questions? Just a quick show of hands. I'm just curious. How many of you have seen the vector equation of a line before? Like that vector form? No? What do you feel? How do you feel about it? Does it seem okay, or?
It's all right.
Yeah?
Is it a complete replacement for the next rival?
It could be, if you want it. See, the idea here, which is really cool, is that this extends beyond 3 dimensions too. Like if you want to go into 4 dimensions, you can, right? It's the same formula. You'd have like x naught, y naught, z naught, whatever you want, not, you know, some other variable.
Besides some of the dot stuff, is there any stuff that actually does extend to 4, 5, 6 higher dimensional stuff?
Other than the dot product, which extends, are there other things that extend?
Dot or cross. So for example, calculus 3 is any correlation to going to higher dimensional calculus.
I'm not sure I get your question. Yeah. We'll talk about it some more. We're almost out of time. We don't have enough time to get into planes, but we can at least start thinking about it. To define a line, we only need what? 2 distinct points. To define a plane, you need what? 3 distinct points, right? So wouldn't it seem natural at this point that I somehow now tell you we can come up with a vector equation of a plane?
Yeah.
Right? I mean, that seems natural. We just started with lines, right? And I said, now we can do vector equations of lines. And now it seems like we should be able to do planes and do vector equations of planes, right? That's not what we're going to do. We're not ready for it. It'll come later. What we are going to do is start studying planes more in the more general form. So how many of you are comfortable with the idea that this equation right here is the equation of a plane? Show of hands. Okay, if you've never seen it, it's okay. I want us to think about this in the last 2 minutes I have. Think about this equation and about the points that satisfy it. If I let x and y be 0, what's z? 1, right? So if I let x and y be 0, we get 1, right? I'm not going to go up 1. I'm going to say that's 1, right? That's 1 point that satisfies that, right? Now let's let x and z be 0. So let x, let z both be 0, and what's y? 1. Okay? And then if you let, where am I? Y and z, let y and z be 0. So let this be 0 and this be 0, and what's x have to be? 1. So we have a point here,